What's up, everybody? Mr. McCarson here with another chemistry video. This time, our topic's going to be nuclear chemistry, which is a really special um, area of chemistry that we teach in introductory chem. This is all about the nucleus and what holds it together, and the very unique types of nuclear reactions that can occur to alter a nucleus. Very difficult to do. Very large amounts of energy are involved, and so this is an exciting topic. I'm glad to present it to you, and hopefully you enjoy it. So let's get started in talking about the power of the nucleus. So our journey first begins with understanding the difference between a nuclear reaction versus a normal everyday chemical reaction. Now, nuclear reactions involve the nucleus. Duh, it's kind of in the title. This is where the number of protons and neutrons in a nucleus get altered. Now, we have a name for this. We call this transmutation. When you change the neutrons or protons in a nucleus, the identity of the element or the isotope may change as a result of those numbers of protons and neutrons changing. The second thing that occurs with nuclear chem is when you alter a nucleus, you are dealing with tremendous amounts of energy. We call this energy nuclear binding energy. And so if you break that nucleus open, you can release that nuclear binding energy. To fuse that nucleus together, you also incorporate large amounts of energy. So we're going to talk about how this works on a variety of scales. Now, if we contrast that with normal chemical reactions, normal chemical everyday reactions, we're talking about single replacement, double replacement, combustion, synthesis, and decomposition reactions. They involve changes to the valence electrons. So, in ionic and covalent bonding, which are the two main types of chemical reactions to produce those types of bonds, we're atoms are actually interacting their valence electrons in unique ways. They're transferring them in ionic bonds or they're sharing them in covalent bonds. But that's not really what nuclear focuses on. Nuclear focuses on altering and how do we alter nuclei, especially those that are unstable. So here's a couple of terms about the nucleus of the atom that are important to remember. The first one is a nucleon. Now, up to this point, we've really just said protons and neutrons in the nucleus, but a nucleon refers to either protons or neutrons in the nucleus of an atom. A nuclide is refers to a specific isotope of an element. So you can say like I have a nuclide of carbon 13, or I have a nuclide of silver 107 or 108. We have isotopes, which we've covered already. So in my class, you should be familiar with this term. But the isotopic notation is going to be an important aspect of understanding nuclear chem. It's a little bit unique for nuclear, but isotopes are atoms of a given element with the same number of protons but different number of neutrons, thus a different mass number. And remember, mass number is important in nuclear chem because some isotopes of certain elements are unstable. They have unstable nuclei due to their mass number being too large or too small. Okay, and then finally, just a refresher, mass number is the number of protons plus neutrons in the nucleus of the atom. And we want to keep in mind that each of those particles of one proton or one neutron is approximately one atomic mass unit. Okay, so here's a refresher on isotopic notation. So in isotopic notation, X represents our chemical element symbol from the periodic table. The superscript in the left-hand side A is the mass number, which is the number of protons plus the number of neutrons. Z, which is the bottom left subscript, is the atomic number, which is the number of protons. And then sometimes you'll see the letter N, and that's just a symbol to represent how many neutrons are in the nucleus of the isotope. Now, when we talk about nuclear chem, it's important to understand that there's like some fundamental forces in nature. And when you go further into the course of physics, you're gonna hammer in on a lot of these different forces with the laws of physics. And so the main force of nature that we're dealing with here, and there's other forces at work always in the universe on these atoms, but it's what we call the strong nuclear force, and it's the force that holds protons and neutrons together in a nucleus. Now, it's important to remember that like protons, as soon as you get two protons in a nucleus, they're both positively charged. And so according to the laws of magnetism and electromagnetism, they want to repel from each other. So the strong nuclear force, when you add neutrons into the nucleus, something happens to where there is an attraction between the neutrons and the protons. It's not quite gravity, it's a little bit more mathematically difficult than that. But suffice it to say that the attractive forces between protons to neutrons is greater than the repulsive forces between protons. And so that allows your nuclei to stay together and stay stable. Now, if this becomes imbalanced, if there's greater repulsive forces between the protons than attractive forces between the neutrons and protons, then that's where you could have radioactive decay and something could break off of the nucleus of your isotope. Now, a couple of other forces, just briefly. The weak nuclear force is the force that is responsible for causing radiation. And this would be like the repulsive force between protons that adds to the instability of the nucleus. If the nucleus becomes too unstable, it will undergo a form of radioactive decay to try and get itself to a more stable isotope. Magnetic force is important because this is the attractive force between positives and negatives, and it's the repulsive force between like charges. So two two positives will repel and two negatives will repel from one another. And then finally, we have gravitational force, which is an attraction that acts between all bodies that have mass. Okay, so to once more hit upon the concept of the strong nuclear force, because this is why nuclear chemistry has so much energy involved in it. Remember that the protons in the nucleus should repel from each other. So, like, if we look at this diagram here, the protons in this diagram are going to want to get away from each other because they're both positive magnets, essentially. However, the strong nuclear force that holds the nucleus together is much stronger than the repulsive forces than the protons. I think of it like a glue or like the neutrons. Like growing up, I would do like we would when you get with the kids in the backyard or you're playing in the neighborhood with your friends, you would have a game where you call it the dog pile. So you would like jump on somebody and hold them down. Not for any malicious purposes, but like that was just the way kids play. We're rough house back in the day before cell phones kind of stopped kids from going outside ever again. But I think of neutrons. When you add neutrons into the protons, they kind of dogpile, if you will, on top of the protons, and this prevents the protons from flying apart from one another due to their repulsion. Now, remember, enormous amounts of energy are required to separate the nucleus into its component protons and neutrons because of this strong nuclear force. Now, there's a way at higher levels, especially if you get into like engineering and quantum mechanics and higher level physics, where you can mathematically derive and explain strong nuclear force. We're not at that level yet, so we're just going to say if we're ever asked a question where like what holds the nucleus together, kind of the simple introductory high school chem answer to that is the strong nuclear force. Why does the strong nuclear force hold it together? Because it's greater than the repulsive force between two protons or more. Okay? And that's our strong nuclear force. Now, what happens when there's instability in the nucleus? What was probably going to occur is a form of radioactive decay. And this is an important term you're going to hear decay a lot. Decay is the spontaneous, meaning it can happen anytime, disintegration of an unstable nucleus into a lighter, more stable nucleus, and the subsequent release of both particles and energy. And oh, there can be a lot of energy. And we have three main types of decay that we're going to focus on in this course for introductory chem. We've got alpha decay, beta decay, and gamma decay. And you can take a look at this little diagram here, but we're going to go into more detail on each of these forms of decay, and you're going to be writing reactions with alpha decay, beta decay, and gamma decay very shortly. All right, so number 138, Nucleon, is going to join me for this little chart here. So this is where we start to talk about the three main types of radioactive decay particles, the most famous of which is alpha. Now, alpha is famous because it's what scientists like Rutherford used back in the early 1900s when we started to understand the process of radiation and radioactive decay from elements like uranium and polonium. But an alpha particle is a chunk, if you will. It's a chunk that breaks off a large unstable nucleus from an atom like radioactive uranium. The symbol for alpha is the Greek letter alpha, and the identity, what alpha really is that it's the same size particle as the nucleus of a helium-4 atom. Now, to be very clear, there are no electrons. So this has got a charge of +2. Okay, and if we actually wanted to draw the symbol for radioactive beta particle, the symbol is 4 for the mass, 2 for the atomic number because there's 2 protons and 2 neutrons in an alpha particle, and then we put He, or you can put the alpha symbol. Okay, so this would actually be isotopic notation for an alpha particle. Now it's important to remember it's like a little positively charged bullet that will break off and get emitted and ejected from the nucleus and fly off. And the big thing is it can hit other things, especially if they're positively charged, and cause a change. Now, penetrating power is the strength of alpha to penetrate other types of matter that exist. And alpha is the weakest of the three, so it can actually be stopped by paper. Okay, so if you hold up a sheet of paper, you can theoretically block alpha particles. Okay, now the next one is what we call a beta particle, which is a high energy electron. And you might say, but Mr. M, how do you have an electron come out of a nucleus? I thought nuclei were just protons and neutrons. You're correct, but something can happen. When a nucleus is so unstable, there can be an emission of a beta particle when a neutron, because an atom needs to change its atomic number or its mass to become more stable, it is possible for a neutron to split, and it will split into a proton, which it leaves behind, increasing the atomic number of the nucleus, and a beta particle, which is a high-speed electron, and that electron cannot exist in the nucleus, and so it immediately gets ejected. And same thing, it shoots out from the nuclei to interact with other forms of matter and energy in the universe. Now, because it's simply an electron, the charge of a beta particle is -1, and it's got a weird symbol. The symbol for beta is 0 for the mass. Now, electrons do have mass, but it's so minuscule compared to protons and neutrons, we still count the mass of this as 0. The atomic number we write as -1, and then you can use the symbol of either B or E, and then this would be your isotopic symbol for a beta particle. And the other way you could see it is 0, -1, B for beta, and that's the Greek letter beta. So these would be the two isotopic symbols that are common, and different worksheets and textbooks use either E or B. Same thing for alpha. Alpha is usually in my class we do 4,2-He, but alpha can also be 4,2 with the Greek letter alpha. Either of those symbols are perfectly acceptable and they're interchangeable. It just depends on your own kind of flavor. Now, what stops beta? Beta has greater penetrating power than alpha. So because electrons are tinier and more energetic and moving faster than alpha, they can pierce through things like paper. What would stop alpha is something thicker like cardboard or heavy clothing, like if you're wearing jeans, jeans could stop beta. Okay. Now the final one, and this is the tiger in the room, is what we call gamma radiation. Now, gamma is non-particle. So if we think about beta, these are like little bullets that fire out of the nucleus. And if we think about alpha, alpha is a larger particle bullet that fires out of a nucleus. Okay, so beta really tiny, alpha much larger. Well, gamma is simply energy, and energy travels in the form of a wave. So gamma, when we say it's a non-particle radiation, it's because gamma is really gamma waves from the electromagnetic spectrum, and they are incredibly energetic. Now, the charge on gamma, there is none. It is a neutral form of energy, and it's got a unique symbol. The mass of gamma, because it's pure energy, is 0, and it's got no atomic number. And we do the Greek letter gamma, so this is the Greek letter gamma, and when you see this symbol, here's how you interpret this. A lot of energy just got released. I'm talking a lot of energy, okay? So that is a gamma. And usually what happens is like when a large nucleus decays an alpha or beta, there's a resulting release of a gamma ray. And that's what, for example, in like nuclear power plants, we use that gamma to heat and boil water to drive a steam turbine. Now, gamma is incredibly difficult to stop. It has really dangerous penetrating power. This is what causes like radiation sickness in humans when they get exposed to dangerous radioactive decay. It's gamma that's actually damaging their body cells, their organic molecules, specifically their DNA. It can lead to things like mutations in cancer. And so the only way to really effectively, like traditionally, stop gamma is with lead. So lead is a very unique element. It's got things that make it dangerous and toxic. But one of the great benefits of lead that protects us still to this day, especially if you ever had something like an X-ray or you plan on going to outer space, is lead can deflect and block gamma rays and X-rays. So these are the three types of radioactive decay: their symbols, their penetrating power, and their identities. Very important to know this chart. All right, so our big thing here is to just go through the different types of nuclear symbols or isotopic symbols for entities that you might see in a nuclear reaction. Nuclear reactions do look slightly different than normal chemical reactions. And they still have products and reactants. That's a big thing. There's still a yields arrow in the middle, and you still have reactants on the left-hand side of the arrow, products on the right-hand side. So first off, we have a proton. Symbol is P plus, and the symbol for protons are usually one for the mass, one for the atomic number, and then H for hydrogen or P for proton. Those symbols are interchangeable. A neutron symbol, the basic symbol is N0, but in an isotopic nuclear equation, you would write it as one for the mass, zero for the atomic number because it's not a proton, and then lowercase n. An electron, okay, so E negative is the simple symbol, but in nuclear chem, you write an electron as zero mass and -1 for its effect on the atomic number, and then lowercase e. Now remember, this symbol is the same as beta, because that's effectively what beta is. The only difference when we talk about beta, beta is specifically coming from the nucleus, right? Like it's been ejected from the nucleus in the process of a neutron breaking apart. Alpha, symbol Greek letter alpha, and then here are the two isotopic symbols: 4 for the mass of the alpha, 2 for the atomic number. Never forget alpha, 2 protons plus 2 neutrons. That's where the 4 comes from. And because there's no electrons, the charge on an alpha is +2. Now I know you might be going, well, Mr. McCarson, when we write symbols for ions, there's usually a positive or negative in the upper right corner. We don't do that in nuclear chem. We just know through teaching and lessons like this that alpha always carries a +2 charge. That's just something you have to store in the back of your mind or keep in your notes. Beta is a high-speed electron that's usually being ejected from a nuclei. And the symbol for beta is 0, -1 with the Greek letter beta, or 0, -1e, the same as an electron. Now, a positron's kind of weird, and we'll talk about this later in class and later video section. But a positron is actually the same mass and similar properties as an electron, but its charge got inverted from negative to positive. Now, we'll go over later why that happens. It's a little weird, but it is a thing that exists in the world of chemistry, specifically nuclear chem, and it isn't that uncommon. And so for a positron, the symbol is the same as beta, but one major difference. In a positron, the charge is +1 in the bottom left-hand corner where the atomic number goes. Okay, so these are symbols you're going to see a lot in our worksheets and in problems on the quiz and test. I'm going to teach you how to write equations and balance with them. So I really want you to focus on making sure you have this chart down. All right, so here's kind of an introduction to writing nuclear reactions with different types of decay. So the first one we have here is an example of alpha decay. So how would this look on a worksheet or quiz? The first thing is we have the mass number up top. and you have the atomic number on the bottom. So that hasn't changed, and we've kind of talked about isotope symbols. Now remember, your reaction arrow is right here in the middle. So we've got the reactants on the left side and the products on the right. Now, the big thing is this. Whatever your mass number adds up to, so whatever the upper number on the left side of the arrow, on the reactant side of the arrow equals, so you see how this is 238. When we look at these two mass numbers for the alpha particle and the new atom of thorium that we're creating, they must add up to 238. Both sides, the mass must be equal. Law of conservation of mass holds in this nuclear chemistry. Now, same thing with the atomic number. If we look on the bottom left side, this is uranium 92. Well, it's going to decay in alpha. Alpha will break off of it, and alpha has an atomic number of 2. And when we add that to the 90 of the thorium that's left behind, what do they add up to? 92. So in nuclear reactions that are balanced, the mass numbers on the top of both the left and right side of the arrow have to equal, and the atomic numbers on the bottom, the subscript, on both sides of the arrows have to equal. And that's how you balance a nuclear reaction. Okay, let's go ahead and take a look at another one. So for beta, same thing happens, but it's a little weird. So in beta, if you notice, we start with thorium, which has a mass of 234. And this is going to have beta decay. So it's going to break off a beta particle from the nucleus. Now, beta has a mass of 0. So when we emit beta, the mass of the new atom is still 234 because 234 plus 0 equals 234. Now, a weird thing happens with the atomic number. Notice how we're starting at an atomic number of 90, right? 90 protons is thorium. Now, when we emit beta, beta is -1 to the atomic number. And so what happens is the new atom we make, Pa, which is protactinium, I believe, if you take 91 and you add it to -1, you get 90. So 91 plus -1 equals 90, and that makes it balanced. So a weird thing happens when there's beta decay, you actually increase your atomic number by 1. The atom gets a larger atomic number and it changes to a larger atom on the periodic table. When you undergo alpha decay, your nucleus will lose 2 protons, so you're going to fall to a atom that's 2 spots lower on the periodic table. And that's kind of a typical trend for both alpha and beta that you'll find. Okay, so let's take a look at gamma. Now, how would gamma look? Gamma is essentially the same thing like in this one. We're still doing the alpha decay of uranium-238 to make an alpha particle and thorium-234. Now, the big thing is when you see gamma, like here, it says 2, and then you've got the gamma symbol. What that means is you're releasing 2 rays of gamma are leaving the nucleus and going into the universe as a result of the alpha decay. It's generating energy. The breaking off of the alpha is releasing a ton of energy. And remember, that gamma is really powerful, really powerful. It's the most energetic wave in the universe. It's why, like, when you watch like TV shows like Fallout and you see those nuclear bombs go off fictionally, it's why there's so much energy. It's all of that gamma being released as those nuclei split apart in the nuclear bomb. Okay, so these are some examples, and once again, they're quick. We're going over these fast. We'll do a lot more in class, and I'll have a video where I do nothing but balance nuclear reactions of a variety of types to give you practice. All right, so one thing we want to talk about is the effect of alpha, beta, and gamma as they travel through a magnetic field. Now remember, a magnetic field is where you have a negative magnet separated a specific distance from a positive magnet, and the area between, so the area between the negative and positive magnets, this region is known as your magnetic field. Now, if you were to fire alpha, beta, and gamma particles straight down the middle of the magnetic field, which particle would actually curve towards the negative magnet? That would be the alpha particle. So number one, this would be the pathway of alpha. Because alpha is positively charged, it's attracted to the negative end of a magnetic field. Okay. If we go to over here to number three, what's going to be deflected or going to bend towards the positive magnet? This would, or sorry, number three would be a beta particle. So this would be beta, this would be alpha. Because of their charges, they're attracted to the opposite magnetism. Now, which one's going straight down the middle and that's unaffected by the magnetic field? That would be gamma. So the one straight down the middle is gamma, because gamma doesn't have a charge, it's neutral, it's pure energy. It's not going to bend or curve or be deflected as a result of a magnetic field, passing through a magnetic field. This is a cool slide to know, especially for a quiz. Hint, hint. All right, I like this slide, just a simple diagram to show penetrating power. So alpha has a good picture here. You can see alpha, how large it is. And remember, the idea with alpha is because it's kind of large and clunky and doesn't move as fast as the other particles, it can be stopped by paper. Beta is a high-speed electron, so being much smaller and energetic, it can go through the paper, but it can get stopped by things like thick wood or jeans, very heavy lab clothing. And then finally, gamma is pure energy. So gamma can penetrate all kinds of matter, including our flesh. And one of the few things that blocks gamma is if this is the element lead. So if this is Pb, then that will actually block gamma rays. Okay, so this is a little example of penetrating power. Once again, a good diagram to know for things like possible test questions. Okay, so it's time to talk about energy and nuclear reactions. And for energy and nuclear reactions, we're going to enter our good friend Albert Einstein. Now, Albert Einstein was the person to famously derive the energy that was released in nuclear reactions. And we call this energy binding energy or nuclear binding energy. So it's the energy stored in a nuclei between the protons and neutrons. Now, his famous equation, E equals mc squared, the energy equals the mass of the sample, or the change in the mass, multiplied by c is the speed of light squared. Okay, and we use this to calculate the energy. And it was a very breakthrough moment in the history of physics and chem, because what it said is that there is a pathway to move between energy and matter. Like matter could be converted to energy, energy can be converted to matter. And this is what happens in stars. Like that's a really big deal for the functioning of our universe. Now, in chemical reactions, the amount of mass converted to energy is minimal. So like in normal chemical reactions, this is not that big of a deal, because normal chemical reactions deal with what? Electrons. And electrons have very, 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 very tiny mass. Okay? Now, binding energies are many thousands of times greater in nuclear reactions. Okay? Thousands of times. You get a tremendous amount of energy from nuclear reactions, whether it's fusion or fission, and we'll talk about the difference shortly. But Einstein, with his famous E equals mc squared equation, did that. Now, for prep level, we're not going to use this actual functionally for mathematics. You'll use it later on when you take courses like physics. But I want you to know that this is where the energy of nuclear equations is derived, is from Einstein, and E equals mc squared. All right, so we're going to take a look for a few slides at a very famous graph. This is known as the band of stability. And real quick, on the y-axis, we have the number of neutrons. So we start down at 0, and then we start from 1. We start working our way all the way up to about 130 neutrons. The x-axis is the number of protons, the atomic number. And once again, it starts at 0, but you'll realistically, you have to have 1 proton, and then you start going all the way up, and this graph goes up to 80. Okay? Now, the idea here is any element with more than 1 proton, so anything but hydrogen, will have repulsion, right? So if you have 2 protons, helium, those protons now want to get away from each other, okay? Now, the strong nuclear force helps keep the nucleus from flying apart. And what this band shows us is the nuclei that are stable. So, what ratio of protons to neutrons allow stable nuclei for progressively larger elements to exist? Okay. Remember, neutrons help stabilize the nucleus, and the ratio of neutrons to protons is an important factor. Now, this red line I want to highlight here, this red line is the 1-to-1 neutron to proton ratio. And so when you start lower, like atomic number 20 or less, most stable isotopes run at a 1-to-1 ratio. However, as you start to approach an atomic number of 30, you notice the band of stability start to bend towards the number of neutrons, meaning that up higher elements require more neutrons than protons. It's not a 1-to-1 ratio in order to get a stable nuclei. All right, so if we're to take a look at this graph, if we look down here at the lower section of the graph, this is where atoms will follow and their isotopes will follow like a 1-to-1 pattern for stable nuclei. Okay, so lower atomic numbered elements have a smaller stable nuclei, have with a neutron to proton ratio closer to 1.1. Not perfect, like it might be 9 protons, 10 neutrons, but it's very close to 1-to-1. As your element starts to get larger and larger and larger, the band of stability, so if we look up here in this upper section of the graph, what's starting to happen is you start to have a need to have more than the number of protons in terms of neutrons in order to keep the protons together. So like the protons become such a large ball of positive repulsion that you start to need to dogpile way more neutrons on top of them to hold the nucleus together. And so what we say is in the upper region of the graph, at the very largest elements, in order to have a stable nucleus exist, you need for every 1 proton 1.5 neutrons. Now that doesn't mean you can put a half a neutron in an isotope. You can't, but it's approximate. So like if you start looking at mercury, lead, bismuth, to get a stable nuclei, you're going to need about 1.5 times the neutrons as you do for the protons. So if you have a number like 80, right? So if you have 80 protons, you're going to need about 120 neutrons to settle down the 80 protons. So you'd add an extra 50% from 80, which is 40. So you get 120 neutrons would be a pretty close number, a pretty good estimate that would make an atomic number of 80 stable. Okay, so the big point of this graph is this shaded region that I'm moving the mouse along. This is known as the band of stability. This is what the graph gets its name from. And all of these little red dots are the stable nuclei that exist for different elements, all the way up to, we're looking at we're looking up to mercury. Okay, and so this shaded region shows nuclei that would be stable, and we call this the band of stability. Now, if your nuclei is above the band of stability or below the band of stability, you will do a different type of nuclear decay or radioactive process, radioactive nuclear reaction, in order to get to an isotope that's in the band of stability. So for example, if you have a nucleus that graphs somewhere here where I put my green dot, this nuclei is above the belt and it has too many neutrons. So it needs to find a way to get back into the band of stability. So what happens here is you tend to decay by emitting beta particles. What it means to emit beta is to actually get rid of a neutron. You split a neutron into a proton and an electron. That electron gets emitted as beta, and then the proton kind of pulls you back towards this band of stability. Now, on the other side, let's say that you have a nuclei that graphs somewhere here, and your nucleus is unstable. It's below the band of stability. What happens is when you're below, you have too few neutrons. You need more neutrons. You need more weight. You're not heavy enough. So these tend to decay by positron emission or electron capture. And once again, I'll talk about both of those processes in a future video where we do actual examples of balancing and writing nuclear decay reactions. But just know that if you're below the band of stability, you've got to get more neutrons, and the way to get more neutrons is proton emission or electron capture. Right, so quick note, uh, there is a limit. So on the periodic table, there's a point at which no stable nuclei are it's actually possible for them to exist. So there are no stable nuclei with an atomic number greater than 83, which I believe is bismuth. Yes, bismuth. Okay, so the atomic number 92 is the last naturally occurring element. This is uranium, very famous. So any element above 92, so from 93 to 118, is synthetic. It's got to be made by humans in a nuclear chemistry laboratory or a particle accelerator or a nuclear reactor. But human technology has got to make those elements, and those are usually radioactive to the point where it's guaranteed at some point they'll decay back down to a naturally occurring element. But yeah, so things like plutonium number 94 is synthetic. It does not exist on Earth without humans creating it. Now, keep in mind, nuclei with an even number of protons and neutrons tend to be more stable than nuclids that have odd numbers. So very famously, uranium, there's uranium 238 and uranium 235. 238, it's an even number. It's more stable than 235, which is an odd number. Now, I like this diagram at the bottom here. So it shows that in a small nucleus, the blue arrows are attraction between neutrons and protons, and red is repulsion between protons. So in a small nucleus, there's much greater attraction than there is repulsion, and so you tend to get really stable nuclei. The smaller the atom, and the smaller the nucleus. When you get really large nuclei, there's way more repulsion between protons. You start to get such a super large group of individual positive magnets, they all want to get away from each other, like Mr. M teaching freshmen. Okay, and however, there's no matter how many neutrons you have, like it's the strong nuclear force becomes weaker and weaker and weaker the more protons you shove in there. And so this is why we get so much radioactive decay among very large nuclei. It's really hard for them to be stable. So I really like this little diagram at the bottom. All right, now a radioactive decay series is simply a series of nuclear decay processes. So, like if we start with uranium 238 or 235, depends on what chart this is, what happens is large radioactive nuclei cannot stabilize by undergoing only one nuclear transformation. So, like uranium 235 is unstable. It can't just undergo one radioactive decay process and be like, oh, I'm happy, right? It actually will turn into, in this case, uranium will turn into thorium, and thorium's still unhappy. So thorium will then turn into protactinium, and protactinium then turns into a different mass of uranium. So you start to undergo all of these steps. You'll start to jump from one atom to the next in a series of either alpha or beta decays is usually what's happening here. And then you go all the way down until you finally get to an element that is light enough that a stable nuclei can exist. And we call this a radioactive decay series, and you might be doing something similar on an assignment soon. All right, so let's talk about my favorite video game, Half-Life. No, we're never gonna get Half-Life 3 from Valve. Maybe one day. But Half-Life, the real Half-Life, is a very important measurement that we know about radioactively unstable isotopes. So half-life is the time it takes for one half of a radioactive sample to decompose or decay. Now, decompose, remember, is a word that it's not like we're not actually losing the matter in the universe. When we say decompose, what we're really saying is that radioactive decay will cause the sample to turn into other types of isotopes. So like uranium 238 will have a half-life, and what that half-life means is in that amount of time, half of the uranium will not disappear from the universe. It will be converted into another type of matter, maybe thorium, okay? So it's the rate at which a radioactive sample decays particles and turns into a new, more stable isotope. And radioactive decays can be very, very long. Like there's elements that have half-lives that are longer than the current age of the universe. They're like over 14 billion years. And there's radioactive half-lives that are in minutes or seconds. So it's very versatile and depends on how unstable the isotope is. The more unstable, the shorter the half-life. The more stable, the longer the half-life. Okay? Now, half-life depends only on your starting amount of nuclear material. So like, do you have 200 grams of uranium, 2 kilograms of uranium? You know, the starting amount is one of the only factors that matters. We call that the reactant concentration. Okay, so here's a cool graph for half-life. Big hint on this one, big hint for this graph. So here we've got percent of radioactive isotopes remaining on the y-axis, and we've got the number of half-lives gone through. Okay, so we always start at a time of 0, okay, and then we count half-lives, or we actually count the time of a half-life, like, 8 hours, 50 days, 3.5 years. It's different for different elements. So we're starting at 100% of our radioactive sample. Now look, once we get to half-life 1 and we go to the graph, at half-life 1, what percent of our original sample remains? 50. If we go down to the second half-life, half-life 2, very good sequel, what percent, what's half of 50? 25. If we go to half-life 3 and we go across, what's half of 25? 12.5. So you see, the pattern is we keep dividing our previous amount of sample by 2. And this can go on forever, right? You keep getting smaller and smaller and smaller amounts of your original sample by a factor of dividing by 2, okay? And this is a nice graph for the concept of half-life. All right, and our last topic, and thank you so much for hanging in this long on the video. I really appreciate your support, and I hope it's been helpful and useful and enlightens you to the possibilities of nuclear chem. But we're going to talk about fission versus fusion. Now, fission is what we are really good at on Earth in terms of our own human-based nuclear chem. Fusion is splitting, keyword splitting, a heavy nucleus into 2 or more smaller nuclei. So you're taking a big atom and you're breaking it apart. Now, this releases a lot of energy. So like 1 gram of uranium-235 is if you undergo fission of that, you get the same release of energy as burning 3 tons of coal without the greenhouse gases. It's 100% clean. Okay, so nuclear energy is the cleanest energy we have available. Until we can do the second one, fusion, nuclear fission is actually a great way we could clean up the planet. Okay, now this also leads us to a chain reaction. Okay, now a chain reaction is a self-propagating reaction. So once a chain reaction occurs, it doesn't stop. And this can be both a great thing for productivity of energy, you keep it going. It can be a bad thing if that is an uncontrolled chain reaction, which is what happened in Chernobyl. Now, critical mass, by definition, is the mass required to sustain a chain reaction. If you don't have enough nuclear material, you can't keep it propagating over and over, essentially, until you stop it. Okay, now, big contrast with that to fusion. Fusion is the combining of 2 lighter nuclei to form 1 nucleus of larger mass. And the big thing is this is what occurs in stars. In stars, we take 2 isotopes of hydrogen and we fuse them together to make an isotope of helium, and this releases a tremendous ton of energy, way more than fission. To be clear, nuclear fusion releases way more energy than nuclear fission. Using our coal example, 1 gram of fusion fuel is 20 tons of coal. Remember, 1 gram of fission fuel was 3 tons of coal. So you're essentially looking at 6 to 7 times the energy, okay? And remember, to get fusion to occur, this is why we can't do it on planet Earth very well. We actually can do it in small amounts, and we can only do it for a fraction of a second. We can't we can't make it self-propagate yet. It's the technology I hope to see in my lifetime. It might change everything on our planet forever. But it's still like the next great horizon for engineers and nuclear physicists. But thermonuclear reaction, why is this usually only occur in stars? Because you need a temperature of 40 million Kelvin to sustain it. 40 million Kelvin. That's hot. That's way hotter than California hot. So that's kind of our great barrier, is how do we contain all the energy in nuclear fusion? And it's not as simple as what Doc Octopus did in Spider-Man 2. And how do we create a apparatus, a machine, a factory that can keep that temperature possible? How do we get the energy to create the temperature to make the energy? Very interesting questions for you going ahead to be our future scientists. All right, so the last slide I want to show you is a basic diagram of a nuclear reactor. Now, nuclear reactors are, if they're done well and they're done with competent companies and individuals and scientists, and they have oversight and regulation, they can provide us with really clean, efficient energy. You want to talk about making an impact on Earth's temperature, build very next generation, high quality nuclear reactors. Now, how do they work in a nutshell? First off, you have your rods. So you have fuel rods and you have control rods. And fuel rods are usually like uranium or plutonium. So you have fuel rods and control rods. Control rods are designed to be like the brake in the gas. The fuel rods are where the radioactive decay is going to occur, and you're going to make lots and lots of gamma rays. Now, you put these fuel rods and control rods in a tank that's contained and usually has many lead shells around it or containment layers to help protect the environment if anything goes wrong in the reactor. And what happens is the release of energy in the nuclear reactions boils water. So in this tank, there's water. This is usually why traditional reactors are near oceans, to help them, number one, cool, and number two, provide steam. Now, the water vaporizes and turns into steam, which rises and will move into a turbine, which is basically a fan that will spin, and it's connected to an electric generator. And this is what produces the electricity to go out into society. Now, that steam will then go through a condenser, which will force it back into liquid form, and that water will get pushed back to the reactor to cool it and then boil again. So it creates this really nice loop of clean energy. And here's the thing here, there's no greenhouse gases. So there's not. There's greenhouse gases associated with wind and solar to certain degrees. Not here. Okay. So very, very cool process. And once again, this concludes my presentation on nuclear chem. I hope you had a good time. If you enjoy this, possibly think about hitting that like button. That would be much appreciated. Drop me a comment below if you have anything that you want to add or say, or any critiques that you can help me with. And remember, above all, don't forget to ever stop studying your chemistry. Have a great day, and we'll see you in the next one. Bye.